Hello friends, this is Vidhan. Welcome to my channel. Today we will see a problem based on commutation relation of quantum mechanical operators. It says, given the usual canonical commutation relations, the commutator AB of A equal to I xpy minus ypx and B equal to ypz plus zpy is, we have four options. So it says find the commutation of A and B where A has been given and B has been given also. So here it says we need to find the commutation of AB where A has been given as I xpy minus y px and B has been given as ypz plus zpy. Now let us multiply I with each terms, so it becomes I xpy minus iypx and this term is ypz plus zpy. Now we can distribute this. This commutation expression can be given by a simplified expression, and this is done by distribution. And this distribution will be given as, if we have A minus B, like here this and this, and multiplied by C plus D, like here this is C and if this is D, then we know that this can be distributed as AC plus AD minus BC minus BD. In this manner we can distribute this commutation relation into four commutation relations. And why can we distribute this? The reason is that all quantum mechanical operators are distributive in nature with respect to addition or subtraction. So first, this term and this term commutation I x p y y p z, then this term and this term, and there will be a plus sign because it is plus and it is plus. I x p y z py, then this term and this term, and there will be a minus sign because minus plus minus. Iypx and ypz, and then minus plus minus and commutation of iypx and zpy. So we have these four commutation relations, and now you can understand that if we want to find commutation of AB, we need to find commutation, this commutation, this commutation and this commutation. So we will find this one individually, let us name it 1. We will find this commutation relation individually, let us name it 2. We will find this individually, let us name it 3, and this 4. So we will find out the solutions of these four commutation relations and we will substitute them in this expression. So let's do the first one. This first one, it is commutation of I x py and y p z. Now I is a constant and we have four quantum mechanical operators x py y p z, and they are in multiplication, and we know what is the formula for, or what is the simplified expression for a commutation relation with four quantum mechanical operators with respect to multiplication. We know that expression is given by we will do it here. We will write here, if we have A, B, C, D, four operators, and these two are in multiplication, these two are multiplication, this commutation relation can be expressed as commutation of A, C, then B and D will come outside, and first B will come and then D will come, plus commutation of A and D, and now B, C will come out, so B will come to right but C will come to left, because C is actually left side, C is towards left of D, so C comes to left, plus now B and C commutation, and when B, C, then A and D will come outside, A will come to left side and D will come to right side, plus commutation of B and D, B, D. Now B and D, now A and C will come out, and since A is to the left of B, C is also to the left of D, so both of them come to left, but first C will come and then A will come, C and A. So here you can see that when both these things come out to the right, first B comes and then D comes, and here when both comes to left, first C comes and then A comes. Okay, so according to this expression we will express this one, first term, and similarly we will express this term when we will be doing this, and similarly this one, and similarly this one with respect to this relation. Okay, so let me write down here. Now I is a constant, so what first we will do, commutation of x and y, py and pz will come outside, and since I is a constant, it can come to the left or to the right, but I will always take it to the left, it is I. Okay, then plus commutation of x and pz, then py and y will come outside, so py here and y will come outside here, and obviously I, plus then commutation of py y, and now x and pz will come outside, x here and pz here, and I will also come outside, plus commutation of now py and pz. So we are expressing this according to this one, and now x and y will come outside, so first y and then x, and obviously I will come outside. Now in our last video we have seen that commutation of two position operators is 0, so this term is 0, plus we have also seen that commutation of x and p is I h cut, but this component should match. So this is the x component of position, but this is the z component of momentum, so this commutation relation is also 0, so the whole term is also 0, plus pyy, and this is minus I h cut. and this is pz, plus this is the commutation of two momentum operators, and we know commutation of two momentum operators is 0, so this term is 0. So what we have from here, we have this minus I h cut, this I, this x, and this pz. Now I into I is minus 1, so minus I square h cut x pz, and I square is minus 1, so it is plus h cut x pz. So this is the solution from the first term. Now we will find for the second term, and in the same way. So first of all we will write the second term here, I x p y z p y here, and we will express it again according to the commutation relation of four operators with respect to multiplication. So it will be given as this x and z commutation py, and this py will come outside, and this I is a constant, so obviously it will come outside, plus commutation of x and py, this py will come outside here, and this z will come to this side, and I will come outside, plus commutation of pyz, and this x will come outside, and this py will come this side, and I will come outside, plus commutation of py and this py, and this x and z will come outside, z first and then x, and obviously I will come outside. Now again, if you see my last video, you will see that commutation relation of two position operators is 0, so the whole term is 0, plus here it is the x component of position and it is the y component of momentum, so this term is also 0, plus this is the y component of momentum and this is the z component of position, so this term is also 0. This component should match in case of position and momentum, plus we also know that if it is commutation of two momentum operators, then it is 0, so all are 0, this is equal to 0. Now we will go to the third relation. Here we have the third relation, and we will write it down. So you can see this is the third relation, iypx ypz. iypx ypz, and again we can give it as commutation of y px pz will come outside, I will come outside, plus commutation of y pz px will come this side, and this y will come this side, and I, plus commutation of pxy and pz will come this side, and y will come this side, and I, plus commutation of px pz, and this y will come outside, this y will come out first, and then this y, obviously both are y, and this I. Now again you can see that commutation of two position operators is 0, so the whole term is 0, plus it is commutation of position and momentum, but it is the y component of position and it is z component momentum, so again this commutation is 0, so the whole term is 0, plus this is again position and momentum and position, but there is a x component of momentum and this is y component of position, so this term is again 0, plus both are momentum operators, so it is again 0, so equal to 0. Now let us go to the fourth commutation relation, and that is, I will directly write down the fourth one is I y p x z p y. So this can be given as commutation of y z px and py will come outside, plus and I also comes outside. Commutation of y and py, this px comes this side and this z comes this side and I also comes outside, plus commutation of pxz, this y comes this side and I also, and this py comes this side, plus commutation of px and py, and this z and y come outside, first z and then y and I also, and again you can see that commutation of two position operators is 0, plus this is not 0, this is I z and y py is I h cut and this is px, plus it is commutation of momentum and position, but x component of momentum and z component of position, so it is 0, plus both are momentum operators, so it is 0. So what we have I h cut and this is px, so I square, I into I is I square, and then h cut, and what we have z and px, this order has to be maintained, z first then comes px, so we have maintained it, z first then we have given px, and these are the constant terms. So ultimately what we have, I square is -1, so minus h cut z px. Now from here we can see that we have found 1 2 3 4, these first two terms are in addition and then subtraction 3 and minus 4. So commutation of AB is, for 1 we have found plus h cut xpz, h cut xpz. For the second term we have found 0, for the third we have found 0, and for the fourth we have found minus. Now one thing, first term is this plus the second term, third term is minus 0, because here we can see minus third then minus fourth, so minus third and minus fourth, and the fourth term is this one, minus h cut z px, so minus minus plus, so finally we have h cut x p z minus minus plus h cut z p x. So we have, if we take h cut as common, we have x p z plus px z z px. Now one thing, that our answer is, actually our answer is C. Our answer is C. Given that answer is the C, and that is h cut x pz plus pxz. But here there is one problem, that we have pxz, but here we have zpx, so they are not the same things. But actually let me tell you that pxz and zpx are same things. Pxz equal to zpx. What is the reason? Okay, moments before I told you that this order has to be carefully treated as it is. The order has to be taken into consideration. If z first, then put z first. If px next, then put px next. But unless and until you require to do some maneuver, the matter is that z and px are the same as pxz, because z and px, if we do commute, it is 0. So when it is 0, that means they commute, and that means zpx minus pxz is equal to 0, and that means this equal to this. So we can write, in place of zpx, we can write pxz also. So hope you understood. So we can write here, answer is h cut into xpz plus pxz. Thank you.